Let's get started. The next parameter we're going to discover is compression stiffness. Now let me show you what kind of example we will work on and then talk about it. I just pinned the top points of this geometry and there is nothing else, all vellum settings by default. Now let's talk about compression. It is the constraint stiffness when being compressed below its initial rest distance. That is, it begins to repel particles when the initial rest distance between them decreases. If we set it to 0, then the cloth should be compressed without any resistance. You see, the wide part of the geometry narrowed without any resistance. As a result, the folds did not form at all. To prevent it from swinging for so long by inertia, I suggest setting some velocity damping so that it doesn't swing for as long as it does now. Let's set up a small value and look again. See, the inertia of the swing now goes away much faster. Okay, now let's take a closer look. Due to the strong narrowing, the geometry became like a tube, and where there is a lot of narrowing, there the points approached each other very much. Therefore, as a result, we have such a non-uniformly distributed mesh. Now let's set a small compression resistance instead of 0 and see how this will affect the simulation. As you can see, the folds have already appeared since we already have a small force against compression. I will reduce the compression stiffness even more and check it again. See, now the folds hardly transform. If you disable the compression stiffness option, then the stretch stiffness value will be used against the compression. That is, the same force will be applied in both directions. You see? No compression at all, because the stretch stiffness value is also taken against compression, therefore such huge folds have transformed. Well, that's all I wanted to show with this example, but I have prepared another example with regards to compression resistance, so let's switch there. Okay, first, let me show you which example we'll be using. Look, the collision tube bends first to one side, then to the other, and drags clothes along, which leads to the appearance of wrinkles. Now I propose to decently increase the compression stiffness and see what changes. As you can see, the difference is not that big. This is because now we have one sub-step, which is not enough to provide strong compression resistance. Well, let's increase the number of sub-steps and look again. See, there is a huge difference. Now there is no compression at all, which is why so many wrinkles appear. Let's look once more. To sum up, the compression stiffness is a good way to control the wrinkles by making them smaller or even more aggressive. Well, now I propose to gradually reduce the compression stiffness and watch how the wrinkles go away. If you look closely, they no longer look as aggressive as in the previous one. We will reduce it even further and check again. As you have already noticed, wrinkles transform less and less. Okay, before we zero out completely, let's scale it down a bit more and take another look. Now they have almost disappeared, but compression stiffness is still doing some job. If we reset to 0, then without obstacles, the geometry will be compressed. I suppose you noticed how easily the cloth was compressed at the very beginning. Even a small force is able to squeeze it. To make this more noticeable, I suggest changing the bend axis so that the collision geometry bends upward. See, compression stops only when self-collision starts to do its job. That is, if you turn off self-collision, then the compression will continue and self-penetration will begin. Good, and finally, let's increase the compression stiffness to the maximum and check again. Now it looks very different. Well, I think we have completely dealt with compression stiffness. We can now move on to the next parameter, which is the stiffness drop-off, so let's get to another scene. Okay, now let's take a look at an example. Look, I only pinned the border points of the two sides, and it hangs from them. Now I want to animate the source geometry so that the pinned points pull the cloth in opposite directions and stretch it extremely. We can do this with a transform node, so let's create one. Now we will disable the simulation and start animating the scale along the x-axis. Okay, let's see what it looks like. Good, we can move on. Now let's enable the simulation and run it. See, so far the pinned points do not follow the animation. Now I'll show you why this is happening. If the source geometry contains animation and you want the pinned points to follow it, you need to check the match animation option. So let's check once more. Here we go. They began to follow. Well, before we start exploring stiffness drop-off, I want to talk about the stretch type, as this is a very suitable example. Okay, now I want to draw your attention to the shape of this stretched cloth. Look, from a lot of tension, the middle of the clothes narrowed quite a lot. If we come closer, we will see that the mesh is not uniform. The triangles are squeezed, especially in the middle. This is the disadvantage of the distance along edges method. Although on many materials, it will look quite natural. Now we will set the triangle stretch method and compare the results. You see? The result is radically different. Now the constraints tries to return the triangle to its original shape, which does not allow them to squeeze so much, and as a result, there are no narrowed in the middle. But now we got artifacts in the form of jitter. Let's quickly get rid of them. First, I will increase the damping ratio. Then I will change the integration method to the first order so that the energy inside the system quickly decays. Good, there are no more artifacts. Notice how uniform the mesh is after such a strong stretch. If we look at the triangle stretch constraint geometry structure, it will immediately become clear how this is achieved. Let's isolate the constraint geometry and see how it looks. I will remove the bend, and there will be only stretch. This is how the constraint geometry looks like. Each triangle is turned into a constraint that keeps the triangle as rigid as possible by removing any stretching or skewing according to the specified stiffness. Now let's switch to distance along edges type and see the difference. You see? No more triangles, every edge becomes a distance constraint that maintains that edge length. Both types of stretch constraints have their advantages and disadvantages. In general, the triangle stretch could result in a smoother look. However, the default is set the distance along edges. Well, we've dealt with the types of stretch constraints. Now, let's get back to the stiffness drop-off. It works completely identical compared to bend constraint stiffness drop-off, with the only difference that instead of angle, it is based on the distance between particles. So now let's set a small value and see what happens. Pick a good viewing angle and then play the simulation. Take a look. As soon as the stretch exceeds the specified distance, the stiffness drops to 0, so there is a break. Now let's set the minimum stiffness instead of 0 so that the particles do not disconnect from each other without any resistance. Look, what an interesting result we got. Let's see once more. Wherever there was a lot of stretching, there the stiffness decreased more, and as a result, such gaps were transformed. To make them more visible, let's visualize the stretch distance attribute. We also need to adjust a maximum distance value. That's fine, let's have a look. See, the gaps are much more noticeable. Well, we can already turn off the stretch distance visualization, then go to the constraints properties, reduce the minimum stiffness slightly, and see what changes. Look, it already looks completely different, comparatively fewer gaps, but they stretches much further. Okay, let's revert the previous value of min stiffness, then I want to show you how to make gaps appear where you want. For that we need to draw a stretch stiffness mask and reduce the stiffness where we want them to appear. So, let's drop down the point wrangle just to initialize the default stretch stiffness value. Then type the following. Float, stretch stiffness is equal to 1. So, now we can drop down the attribute paint node and start editing this attribute. Let's enter the name of the attribute we are going to paint. Then set the value we need and start drawing. Look, in these painted places, we will have a weak stretch stiffness, which means they will stretch more, ultimately their stiffness will drop much faster, and gaps will first appear in these places. So, let's check what we get. Here we go. The gaps appeared right in the places where we decreased the stretch stiffness. Let's see again. That's it, we can move on. Now I want to do something more interesting using stiffness drop-off. Since we no longer need the painted stretch stiffness, let's delete them. Then deactivate the scale by attribute option, as well as disable the stiffness drop-off. Okay, now let's decently reduce the stiffness and see how it looks. Look, we got a very stretchy cloth. So, now I propose to create another distance constraint, which will be generated only on selected primitives and will have different stretch stiffness. Make sure that selected distance along edges. This constraint will have the maximum stiffness. Let's also enable the stiffness drop-off and set it up. Now we just have to specify the source points where we want the secondary distance constraint to be generated. Choose the brush selection tool, then start drawing. Okay, let's back to perspective view and then hit enter. So now let's isolate the second distance constraint primitives and check them. Temporarily disable the main constraint and have a look. As you can see, the constraints were generated only in the selected places. Well, let's go on. Now it's time to check out what we have. See, what an interesting result we got. Where we created a secondary distance constraint, we have a lot of stretch resistance there, and cloth hardly stretches. But since the stiffness drop-off turned on, eventually, the stretch stiffness drops, and these overstretched gaps appear, leaving the impression that the clothes are torn in these places. Okay, let's increase the stiffness drop-off distance and look again. Now the overstretched gaps appear a little later. Well, this time on the contrary, let's reduce it and then compare. I also want to slightly increase the min stiffness. Now the gaps happened much earlier, and there are a lot of them, since we have increased the min stiffness. To summarize, it turns out you can create a stretch constraint as much as you like, and each of them can be configured in different ways like we recently did with bend constraint. So, that's all I wanted to show with this example. Now I propose to move on to another example, and we will already look at the stiffness drop-off and increasing mode. Well, this time we will also use the plane, but in other circumstances. All vellum properties by default. Now I want to create a simple animation. For that, let's drop down the transform node. Put it here. Then we are going to drive the translate Y with motion FX. I will use a sine wave. Let's tweak the period parameter to reduce the sine frequency and see what we get. As you can see, it moves up and down in a sine wave. Well, in general I am happy with this. We can move forward. Now I want to pin some points to the animation. Let's switch to the top view, then choose a lasso tool and select round on center and hit enter. In order to see the pinned points, let's go to the vellum solver and turn on the pin to target visualizer. We will also increase the number of sub-steps. On the properties of constraint, let's only increase the damping ratio. The stiffness drop-off we will leave disabled for now. Okay, let's check what we have. As you can see, it does not follow the animation because we forgot to check the match animation option. So, let's play again. See, we have almost no stretch cloth, which is why it reacts so calmly to such movement. Now I propose to activate the stiffness drop-off and see what changes, but this time we will work with the increasing mode. So, to begin with, let's put 2 and see how it looks. Look, it's already begun to stretch, but as long as it reaches the specified distance, and after that, it immediately becomes non-stretchable as the stiffness increases to a maximum. This is a good method to add activity to the simulation while still controlling the amount of stretch. Well, now let's double the drop-off distance and see again. See how organically it now stretches because the stretch resistance grows from 0 to maximum at a given distance instead of statically applying the same amount of resistance all the time. Without stiffness drop-off, you cannot achieve the same result. Okay, let's increase the stiffness drop-off even more and look again. Since the interval from 0 to full stiffness was increased, it began to stretch more. Now let's visualize the stretch stress attribute and watch when the maximum stiffness is applied. Find the frame where it is stretched and start editing the maximum value. So, let's take a look. You see, stress increases as it begins to stretch. Okay, and the last thing I want to do is set a small value for the stiffness drop-off and see how this affects the simulation. Now it stretches almost imperceptibly, but it generally adds a bit of activity to the simulation. Well, that's all I wanted to show in this example. Now I suggest ending this lesson here. In the next lesson, we will continue to explore the rest of the stretch constraint properties. See you in the next lesson.